welcome to the deep dive. Today we're looking at something absolutely fundamental to our modern world, propylene.
That's right.
If you've touched plastic, worn certain clothes, used specific chemicals,
Yeah.
well, you've encountered something made from this key building block.
Absolutely essential.
But here's the catch. Producing it generally needs really, really expensive catalysts. We're talking precious metals, mostly platinum. And that's not just about the money, right? It's a huge hurdle for making industry truly sustainable.
Exactly. It's like needing, gold to make everyday plastic bottles. That gives you a sense of the dependency on these scarce materials.
Yeah.
So globally, there's this intense search happening. Scientists everywhere are trying to find alternatives that are efficient, yes, but also earth abundant. We need to move away from relying so heavily on, petroleum and these precious metals.
Yeah.
Greener supply chains, more reliability. That's the goal.
Which brings us perfectly to our focus for this deep dive. That's a really exciting development, actually. A new catalyst based on cobalt zeolite called CoS1.
Right, from Professor Jianping Xiao's group.
Exactly, at the Dalian Institute of Chemical Physics. And they're making some pretty bold claims, essentially saying this moves us beyond platinum.
It's a big claim.
It is. So our mission today is to unpack this. How did they make this cobalt catalyst? Apparently using a hydrothermal method, sort of a high-pressure, water-based technique.
Which is key, apparently, for getting just the right atomic setup.
Yeah.
Making sure only these stable tetrahedral cobalt sites are left.
Right. And the big question, how does it actually manage to outperform the standard industrial catalyst, the platinum tin one, PtSn Al₂O₃?
That's the core of it.
Get this. It hits a propylene productivity of 9.7 kilograms per kilogram of catalyst per hour.
That's seriously impressive.
It really is. It's not just a small improvement. It significantly beats the current platinum catalysts, and with a material that's way cheaper and much more available.
And the really interesting part where it gets fascinating is understanding why it works so well, down at the atomic level. Absolutely. And the level of detail they managed to get is remarkable. They used advanced computer simulations, think DFT, density functional theory, and ab initio molecular dynamics, basically letting them watch the atoms react.
Yeah.
And they found something quite profound. The zeolite framework itself, the structure holding the cobalt, it's flexible. And this flexibility actually lowers the energy needed for the key chemical step, the dehydrogenation.
Huh. So it's not just the cobalt atom doing the work, the whole structure around it helps. That seems almost counterintuitive. How does that flexibility lower the energy barrier?
Yeah, it's fascinating. It comes down to something called entropic effects, which sounds complicated, but think of entropy as a measure of disorder or freedom.
Okay. Like a messy room has high entropy?
Sort of. Here, the flexible zeolite structure allows the molecules involved in the reaction more ways to arrange themselves, more freedom of movement along the reaction pathway. This increased disorder or flexibility actually lowers the energy hump they need to get over. It makes the whole process smoother, energetically speaking, even smoother in this specific aspect than for the platinum tin alloy. It's like the zeolite creates a more efficient molecular dance floor.
That's a great analogy. Okay, so this atomic level efficiency sounds fantastic. But does that mean it's faster overall in the real world compared to platinum?
That's a really important question. And the microkinetic simulations, which model the overall reaction rates, showed a bit of nuance there.
Okay.
While CoS1 has that lower energy barrier for the key step, its initial overall reaction rate is actually slightly lower than platinum tin.
Oh, why is that?
It seems to be because propane molecules lose some entropy, some freedom just getting into those narrow zeolite channels. So the concentration right at the active site is a bit reduced initially.
I see. A bit of a trade-off there.
A slight one initially, yes. But, and this is huge for industry, CoS1 shows excellent long-term stability.
Right, and stability is often where new catalysts fall down in practice, isn't it? They just don't last. What makes this one so tough?
Exactly. The big killer is usually coke formation, basically carbon gunk building up and blocking the active sites. Think soot in an engine.
Yeah, clogs everything up.
But with CoS1, something really clever happens. The propylene product, once it's formed, doesn't stick strongly to the catalyst surface. It's called non-bonding adsorption. Meaning it can detach and leave the zeolite pores really quickly, rapid product absorption. And because it leaves fast, there's much less chance for those unwanted side reactions that form coke to happen.
So it almost cleans itself out quickly.
In a way, yes.
Huh.
It prevents the buildup that kills other catalysts. This keeps it active for much, much longer. It's a massive advantage.
That really does sound transformative for practical use. Less downtime, more product over time. So let's bring this home. What does this really mean for you, listening? If this cobalt-based zeolite can replace platinum in these huge industrial processes, what does that signal for sustainable chemical manufacturing, for our reliance on these scarce, precious resources?
It's potentially huge.
It really makes you wonder, doesn't it? How many other common Earth-abundant elements are just waiting, holding similar keys to unlock breakthroughs like this, helping us build a more sustainable industrial future?